I know. Oh, okay. I might ask her for just if they know your contact.
I did so bad. And I regret it. All right, happy Tuesday. So I feel like I'm kind of the bearer of bad news this morning. So first of all, I got word that the caves trip, they're not offering like any tours at all currently because of the federal hiring freeze, whatever, yada yada. So that really sucks. So they told me they didn't even know when the caves are going to be open. So we can't do the caves trip. Yeah.
Can we organize a petition to create a state organization that oversees the caves?
I mean, that's what the Oregon Caves is for, right? It's a national park, but yeah, so they're not going to be open. Some thoughts, I just found this out like last night, so I've been kind of like scrambling mentally. Something we could do is a Crater Rock Museum. I know that's like way less exciting, but just kind of throwing that out there. So we could still take, the class time that we're going to do, like take it Thursday. If that works, maybe skip out on class. But I haven't like contacted anybody at all. Other thoughts, because I'm just trying to think like who else is in the area. And there's like Nielsen Water Company. I just don't think it'll be like that exciting. And we already went to SOU and like saw a bunch of boxes that do things. And so I think like Nielsen Water would be kind of similar. Same thing with like there's the Ashland Field and Wildlife Center. I could contact them, but the same thing, it's going to be like a bunch of boxes that do stuff. So maybe not the most exciting experience since you, again, saw that at SOU. So I don't know if people are feeling the Crater Rock idea. The other thing that kind of came to me right now on a whim is, I don't know, like maybe we could do like I would call it an ice cream lab, only because I guess I have issues with ice cream. And what I mean by that is I am perfectly convinced scientifically that liquid nitrogen is the best way to make ice cream. And so we could maybe kind of test this out, and we could test out liquid nitrogen ice cream, and kind of why, not to go down the rabbit hole of ice cream making, why I love liquid nitrogen ice cream so much is you can like turn anything into ice cream, because if you use like a old-fashioned machine like with the rock salt, you kind of can't use everything, right? If it's too watery, it won't freeze. Same thing, like that's how you make boozy ice cream. Not that we would do that in class, obviously, but again, right, freezing point depression, so you got to get it lower, so that liquid nitrogen. Not to mention, so also why I'm obsessed with ice cream making, I have one of those Ninja Cream Eyes, and then I just get upset about it because it has large crystals, so obviously with liquid nitrogen, you do the fast freezing, so you get really, 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 really small crystals, which obviously gives you really smooth ice cream, versus if you're making it at home in the Ninja Cream Eye like I do, right, it freezes and you have these larger ice crystals that in theory the cream eye breaks up, but not as smooth as the texture of liquid nitrogen. Anyways, sorry, ice cream rant. Did you want to?
There's this really cool lab that you can, or experiment you can do where you take kind of like a large tank, like a fish tank. You fill it up with gas from, I think it's like a super cool gas of alcohol, like ethanol, and you can take like a radioactive isotope.
Oh, we're going to do that on a small scale. So we'll do the cloud chamber experiment that he's talking about. We'll do it on a mini Petri dish scale, so that is coming up in our radioactivity lab. So yeah, you can play with that too personally if you're super excited about it. You can help me make the witch's brew of, like you mentioned, trying to get really cold. We use isopropanol and make the clouds, and then we'll see the little radioactivity. But yeah, so let me know. I don't know what your thoughts are right now, if like the Crater Rock Museum seems cool, or if we want to just eat ice cream and be fat. No.
I like the Ashland Wildlife.
So vote for Ashland Wildlife, so I'll put that on there too.
What's at the Crater Museum? Like, what do they want to
So it'd be the Crater Rock Museum. So right, they have all the rocks. So we could kind of tie that to inorganic chemistry and like the structures and how kind of like the impurities lead to the colors. But, so that's, yeah, we can at least tie to chemistry and inorganic chemistry and colors. But yeah, this would be good. And I have had students in the past who have worked here, and I'm not quite sure what they do, but I know they like study like their food habits from the, I don't know, different isotopes, and yeah. Any other thoughts, votes? Do we like, yeah.
There's a wildlife forensics lab in Action.
Yeah, I think that's what the one she's talking about.
Oh, yeah.
So,
I went there when I was in, I think, middle school. It's very cool.
so maybe, so I'm hearing lots of votes for the Ashland Forensics Lab, or Fish and Wildlife. I don't know, it has a huge name. Forensic Fish Wildlife Lab. So yeah, maybe I'll try to contact them ASAP and kind of feel them out and see what they say. Otherwise, I'm happy to take more votes and opinions on the Crater Rock or ice cream or any other fun things. And so then I have more. So this is either good news or bad news for y'all. So as you may have noticed, I'm getting slowly fatter. So I'm obviously due for a baby. And then unfortunately, my OB wants to go on vacation. So that means that I'm forced to have my baby, assuming that nothing happens. But trying to make it to finals week now is the plan. And so that obviously means that we can't have a final on finals week, unfortunately. But so this is where you guys might like the alternative plan. Is my thought is I might give you the final, so then it would turn into a take-home final, right? So the final that I've given in the past, obviously, yeah, so, you know, I can't give an in-person review. There's lectures and reviews from the past that you could watch. But yeah, then I would kind of probably give you the exam week 10, ideally have it due back like on the Friday of week 10, again with the thought that it's open note, take home, so you can take plenty of time with it, you know, kind of do that week 10. And we may pull back on the polymers biochemistry or just kind of have that in the final, because again, not to kind of talk too much about the final, there's the main thing in there that's like difficult is making this amino acid chain. And that's like the main thing to take away from biochemistry and identifying polymers. So you can kind of learn this last week while taking the exam, which is again like not ideal, but not the worst thing in the world, because it really does help to have those notes for those chapters. So yeah, so that's kind of the plan tentatively, if people are okay with that, with the take-home final kind of the week before, and then I'll probably try to get your grades in hopefully before the finals week. So yeah, that's on the docket. So take all right, other questions? So yeah, I expect the syllabus to be adjusted a little. Like I said, I'll figure out, so I'll call or contact, email Ashland Wildlife Forensic Lab, see what they say, and yeah, we'll go from there. And then, oh, with your papers, last quarter I just kind of gave everybody completion credit, and then so I'll be working on giving y'all detailed feedback. And then if you want to meet with me, I think like meeting individually, even briefly, you know, at any point could be good. I would just shoot me an email and we can like set up a time, probably like in this week or next week, kind of start thinking about your paper. Because at least we'll have that kind of party celebration thing at the end. Yeah.
Is the paper going to be due at the same time the finals?
Probably is how it'll end up. Yeah, so probably a lot of things will be due kind of on that week 10 Friday, ideally.
So it'd be Friday the 6th?
Let me double check the calendar. Yeah, that sounds correct. So yeah, Friday the 6th, probably when the papers would be due. And I would still accept late stuff like over email. So, right, I'll still be checking email and stuff. But yeah, just we can't meet physically, unfortunately. All right, other questions, comments? All right, so let's dive into our chapter, which is really just a continuation of these equilibrium concepts. And so now we're just applying it to solubility. And so now we're really getting into like the why of those solubility rules. So I don't know if you still have your solubility rules notes. You might find them somewhat helpful. You probably don't really need them. And well, let's actually just pull up some of those solubility rules. Trying to find one that I like. And so kind of thinking back again to how these solubility rules read, and I know this one is not the greatest, but the point that we're trying to point out is on this solubility rules, if again, right, from a more simplified aspect, we have this weird kind of ambiguity, right? We're like, oh, this one's moderately soluble, right? The barium salts are kind of soluble, like moderately insoluble. So some of those, right, especially the barium, calcium, magnesium sulfides, right, they're kind of like semi-soluble. We get ambiguous rules. And so now this is getting into the detail, right, the actual solubility, and we're getting a greater understanding. And so now, and in hindsight, maybe I should have brought these chemicals, but if we can remember a typical reaction, so I'm definitely going to do a demo on Thursday, so maybe I can bring this stuff then as well. But like recall, so we have our silver nitrates. Remember, nitrate salts are always soluble. And then if we do our double displacement precipitation reaction, right, we found that we mainly made this cloudy solution. And then if you kind of remember doing those experiments, even then sometimes you would get almost like weird results, right? Like sometimes it wouldn't just powder out. It might look a little cloudy or murky. And so all of that has to do with this degree of solubility, right? So we have this statement that these ionic compounds dissolve to some degree. Obviously, we have the most extreme of sodium chloride, where we can really load up a solution. Obviously, there is a saturation limit. But then other ones, such as silver iodide that we see, these have, right, such a low solubility that we classify them as generally insoluble. So again, that's where we get our basic kind of solubility rules. But again, right now we're just going to learn how to quantify it deeper. And we can even start thinking about like water chemistry, water purification.
What's the exact cutoff at which ionic compound is considered insoluble?
I mean, that's kind of the problem. That's a judgment call. Because we can look it up, right? We could put these in context. We'll look at the KSPs. So that will kind of give you some of the context of that. But yeah, that's where the ambiguity is. And so again, right, we're going to apply our basic equilibrium, remembering that the solid is not part of the equilibrium expression. And so that will give us our KSP. And so again, KSP is just our specialized, right, equilibrium for solubility. And so now we get our expression. So our KSP, so our solubility product constant. And so of course, you can see how this dissociation goes. So we have our ionic compound dissolves into, of course, N equivalents of M, and then M equivalents of X. Yeah.
Say you end up with an element that's like a diphotic, or where it forms pairs like nitrogen. Does that will still apply?
Yeah, so everything, right, just like before, and actually we didn't really belabor this too much, but maybe we should go back and do it kind of later. But like, right, with every triprotic dissociation, right, so you have a triprotic acid, you could set up, right, your equation each time. So that's all you're doing each time. It's like you could set up, okay, I have my first dissociation, here's a KSP.
I didn't mean like triprotic in terms of acid.
Right, right, but it'd be the same concept. So we'll get to that because we're kind of building on that, right? Because we're both thinking of solubility and things disassociating, but then you're probably also getting into things forming together, which is part of this chapter of what it's called the KF, so our product formation, right? So tendency to form like ligands and other things. And so it's just building upon these complex systems, right? We're still kind of doing the same fundamental thing, you know, plus as X minus X ultimately. But yeah, our systems may ultimately get more complicated. And so that's like, you know, once you get into more complicated systems, then you can set up like computers and blah, 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 right, all your variables and map that out. All right, so then, right, we said they disassociated into their appropriate proportions. And then just like before, we need to take it to the power of our coefficients. And again, right, note your solid, not part of the expression. Again, just like we learned previously, right, our solid clump doesn't matter. So not part of equilibrium. And just trying to think back to our equilibrium fundamentals. So then this is our generalized expression. And so it makes the most sense if we look at our example here. So we have, of course, lead 2 chloride. And then it's going to disassociate. So, of course, 1 equivalent of lead, 2 equivalents of chloride, and then our KSP expression. So lead to the power of 1, obviously, and then chloride to the power of 2 there for the coefficient. So just like before, right, with our generalized equilibrium expressions. Oh, sorry. And so this, again, kind of goes back to your question of like how soluble. And so all these things are things that are considered, right, some sort of slightly soluble or, again, everything kind of can be quantified with a KSP, but these are going to be smaller values. Obviously, right, they have negatives, some are very negative. And so this gives you, again, some sense, right? So calcium sulfate, KSP, so that's a little higher, right? So we usually say calcium sulfate is like kind of soluble, and these calcium ones tend to be a little like milky, I would almost say, when you look at them. And again, right, that kind of indicates it's like semi-soluble. And then some of our other ones are pretty insoluble, right, like lead sulfide, silver iodide. So, right, we see that as pretty insoluble. So that kind of makes sense. So that kind of helps us, again, quantify this. And this will be a good reference chart if we need KSPs. Of course, on an exam, I'll give them to you. All right, so this is just one representation, right, of, again, how soluble something is. And now we want to look at perhaps another way to quantify it or another way that you would see it reported. And so now we have to understand how to go between these two. So this is molar solubility. And so again, solubility is just the amount of solute that will dissolve in a given amount of solution, usually at a particular temperature. So again, right, you can look this up on any information page about any compound. We could pull up a Wikipedia page and kind of compare the data there. And so, of course, we may be interested then in our molar solubility. So our molar solubility is just defined as, of course, the number of moles of solute that will dissolve in a liter of solution. And so then we want to figure out how to go between them. And so I'll kind of give you the formula, but then we'll kind of work it out with the rice table and see how it's similar. And so, okay, they just give us the formula here. So we're saying, again, we have our product, and then our molar solubility is equal to this. But let's run through it. Because again, you can take this formula. I just don't like it because it's not intuitive to me. And so let's run through it.
The lowercase n and m represent the number of atoms of each element in the molecule.
Correct. So how many ions dissociate? So let's go down and practice it for our lead chloride here so we can see this a little more clearly, and then we'll see it in the formula. So we have, and again, right, we could set it up just like our rice table. So same format. So write out our reaction. So our reaction, of course, in this case is just studying the solubility. So how much is solubilized. And so just making sure we all follow, right, 1 equivalent of lead, and then of course our 2 here. So 2 equivalents of chloride. And again, right now we're thinking in the context of rice. And so we have our initial concentration, right, our initial molar solubility. So that's basically kind of what we're trying to get at, right? And so I'm just going to kind of put it as S here. And again, we're keeping in mind, though, this is not part of our equilibrium expression. We're just saying, okay, we start with our molar amount to be calculated. Now we can think about the change. And so we might want to put, 0, 0. And again, kind of thinking about the future, we're going to have common ion effects, just like we did with pH, right? Again, just thinking about our buffer. Then our change, so we're going to have, obviously, again, that's not part of our expression, but this will be plus S, whatever our molar solubility is, plus 2S, right? And of course, plus 2, since it's 2 equivalents, right? So 2 dissociate.
It's a total of 4 times more chlorine.
Yeah, with our, well, the 4 will come out in the expression because, yeah, we'll square it. So the rate, so then, yeah, plugging this into the KSP. So I'll put it just generalized first. Right, so this is our KSP expression. Then we have to plug S and 2S in. So KSP equals S times 2S squared. And then, so that gives us 4S to the third is equal to our KSP. And so again, continue. So now algebra to solve for our S here. So sorry, let me pull our value. Where's lead chloride on here? There it is. Sorry, blind. So lead chloride, lead 2 chloride, 1.17 times 10 to the negative 5th. So let's plug that in. So 1.17 times 10 to the negative 5th is equal to 4S to the third. And so now, right, just algebraing is equal to 1.17, oops, squirrely there, times 10 to the negative 5th over 4 to the 1/3 root, or the third root, sorry, wrote that wrong. And so we can take a pause for a second, so I'll let you write that down. And so, if we look, remember our formula, So we could compare this now to the formula. So let's do so. So I just like to compare. So just kind of compare to formula. So again, our formula was given that S is equal to N plus M root KSP over N to the M over M to the M. And so yes, right, that worked out. So our N is 1, M is 2. So we end up with M plus M is 3. So, oh, there's that third root, KSP over, so 1 to the 1, 1 times 2 to the 2. So obviously over 4. So that matches, right, with what we got with our rice table. So showing you either method works. Again, I personally just prefer the rice. I don't know why. My sanity. I don't know why. I don't like plugging into that formula for some reason. Either way, you get the same answer. And so let's just plug that in. So 1.17 times 10 to the negative fifth divided by 4. And then cube root. And so we should get a molar solubility then of 0.0143 molarity. So that's how we can go back and forth between the two. Or figure out, right, our molar solubility from our KSP. All right. And so again, right, molarity is related to KSP. We can't always compare values. And so, right, for our values to be compared, the stoichiometry has to have the same dissociation. So that's where kind of the molar solubility, right, is better for universal comparison. So let's try another one. So let's see if you can do a little practice. Oops. So let's kind of compare. So now let's find the molar solubility of silver chloride. And I have the KSP of silver chloride is 1.77 times 10 to the negative 10. So try that on your own. Feel free to use the formula. Feel free to use the rice table. All right, so what do we get for our problem? So again, I just like using the rice table. It helps me just understand things more clearly for whatever reason. Otherwise, right, you would have gotten the same thing with the formula. N and M are both 1. So looking at our formula, right, divided by, so KSP divided by 1 to the square root of n plus m. So that leaves us with the same formula. So what do we get for our molar solubility?
1.33 times 10 to the fifth, to the negative fifth.
To the negative fifth. Excellent. Everybody get that? Questions on it? Ask questions now. All right, sounds good. And so, just like I teased, we have the effect of the common ion on solubility. And so again, right, this kind of makes sense. Again, kind of think back to the buffers we just did, right? You have to figure out how much do I have initially of my 2 salts. And so same sort of thing. So the addition of a soluble salt that contains one of the ions of the insoluble salt decreases the solubility. And so, right, we can also think about Le Chatelier's principle with this. And so right now we're thinking of our lead chloride equilibrium expression again. So of course we have lead 2+ ions in solution. We have chloride ions in solution. So again, thinking back maybe to that iron thiocyanate lab, right, the shifting. And so we're thinking about, okay, if we add chlorine to it, or more chloride, I should have said chloride to it, then it's going to shift it to the left, right, forcing more solid. So more lead would come out of solution to pair with that chloride. So that would decrease our solubility. All right, so let's see if we can calculate that. I guess we should, let's work through it together. But we're going to see it's pretty similar to our rice setup, like we're hopefully feeling really familiar with. And so let's get out, we need our KSPs. Let me go look at our table here. So calcium fluoride, 1.46 times 10 to the negative 10. Okay, so that's our KSP, calcium fluoride. And so again, right, lay out your reaction. So calcium fluoride dissociates to make 1 ion of calcium to a fluoride. And then, right, initial conditions. So we have some amount. And again, right, watch this. So in this case, right, sodium fluoride. So we're only going to make 1 equivalence of fluoride, right? So what if it had been 0.1 molar of magnesium fluoride, right? How would that have changed? So think about how you would have made 2.2 molar equivalents in that case. So just kind of watch that with all these dissociation problems. So in this case, again, we just make 1 equivalent. So we're starting with 0.1 molar of our fluoride. And so now thinking of our change. So again, trying to figure out our solubility, just kind of keeping this in our mind, but not part of the expression. And then change. Again, we're trying to see how much is in solution. So plus S plus 2S. Again, right, don't forget that we make 2 equivalents of fluoride. So now our equilibrium expression should look pretty similar to what we've done in the past. So of course that leaves us with plus S, and we have this 0.1 plus 2S for our molarity. So does that make sense so far, the setup? I just want to pause there. So ask questions. So, right, does this kind of make sense, kind of what we've been doing, right? Initial conditions change. Okay, perfect. So now we're ready to set it up or do the algebra. And so let's just plug it in. Again, be careful with all the little squaring and stuff. And so I'm just writing out explicitly my KSP, right? Don't forget that we have to square the fluoride. And so then we get S times 0.1 plus 2S squared. And so we could probably make a safe assumption again, like we've done. So again, I'm kind of comparing our change in S value compared to our initial molarity. I'm looking that this is pretty tiny, so it's probably going to be a pretty small molar solubility. So let's make a 5% assumption. And obviously, right, you're more than welcome to do the FOIL, first, outer, inner, last. That doesn't feel too fun to me.
Are we going to have any problems that utilize kind of concentrations like this without, where it's greater than 5%, we have to fill it up?
Potentially, yeah. I can't guarantee that we won't. So yeah, in this case, though, we'll make it easy. So then we're given S. KSP is equal to S times 0.1 squared. And so let me plug it in. I've got my value already. So 1.46 times 10 to the negative 10. So let's see what that gives us. So I get 1.46 times 10 to the negative 8. And then, right, we should double check the assumption. I mean, mental math could have told us it was correct, but just to be explicit, 1.48 times 10 to the negative 5%, so kind of crazy. So let's just do our check over here, because we want to show that, yes, we checked that our assumption was correct. So yes, absolutely small. And then again, let's write our answer. So 1.46 times 10 to the negative 8 for our molar solubility. Questions on that one?
Is KSP like is it strictly an empirical value the same way that the other constants are?
Yeah, I mean, sorry?
Are we going to have to calculate the actual constant in any situation?
Potentially. Again, I can't guarantee anything. All right, so let's look at other scenarios. And so now we want to look at the effect of pH on solubility, which again we'll do a demo with as well. And so the hydroxides are not always straightforward. And again, we'll see what we mean by that on our demo on Thursday. And so we have our insoluble hydroxides. So of course, in general, right, the higher the pH, the lower the solubility. So that makes sense, right? So just thinking about it from the simple equilibrium, right? Obviously, if you have more hydroxide ions in solution at these higher pHs, that's going to shift the equilibrium back to the left. Again, right, kind of thinking of Le Chatelier's principle. And then, of course, at lower pHs, right, the higher the solubility, we could even think about maybe we have to do some sort of reaction and see how much HCl and hydroxide, right, are neutralized. Again, kind of depending on the situation. We don't know what we're going to encounter necessarily. So just kind of looking at that. And so again, so now insoluble ionic compounds that contain anions of weak acids, the lower the pH, the higher the solubility. And so again, just looking at that. So this is just, well, actually, so right, let's look at what this is talking about, because this is, right, now going into kind of environmental chemistry and, right, even thinking about what we would have seen at the caves and everything. And so, okay, what is this saying? So we have a carbonate salt, and what's the common carbonate salt that's found everywhere?
Sodium bicarbonate.
So we have sodium bicarbonate. Although I wasn't thinking of it, this one, but that one's probably a good one because it said M2. But what would be another one? Another carbonate salt. So if it's not sodium, what's another common one? That the sea creatures are made out of?
Is that a calcium carbonate?
Yeah, calcium carbonate, because that was the other one I was thinking of, right? So you want to kind of keep this in mind too. Again, right, focusing on the carbonate, because eventually that can become hydrogen carbonate or, right, carbonic acid. So just kind of thinking of all of those. We just want to keep that in mind. And so again, right, we're thinking about this solubility. And so we have this dissociation, so the lower the pH, the higher solubility. So, right, these carbonates tend to react, of course, and then they can form hydrogen carbonate like we've seen. So, of course, we have our dissociation. Then this gets into, right, pH. Okay, well, that carbonate goes on to make hydrogen carbonate, which we know is amphoteric, which can then make carbonic acid. And so this is all to say, right, everything is one big equilibrium. And again, right, kind of thinking about how the environment works as one big buffer solution eventually, right, your animals and limestone. So like, right, little sea creatures are made of calcium carbonate. Limestone is calcium carbonate. So you have a lot of sources, especially the limestone. So there's plenty of limestone in the ocean. So there's lots of sources of carbonate, right, to neutralize, again, this low pH. So again, thinking about how that will react and disassociate. And then again, make carbonic acid eventually, but of course, everything is just equilibrium reacting.
Is there any such thing as a magnesium carbonate? Like
Probably, yeah. It's just, I just pointed out calcium, right? Because calcium's the limestone, so that's your big reservoir in the ocean. All right. And so now this kind of gets a little tricky. So we kind of have to think back to, right, whether a salt is acidic, basic, or neutral, if you kind of remember that, right? That was like the tail end of chapter 20. So take a moment, let's just focus on barium fluoride for a second. So just kind of think about barium fluoride. Let's think about that for a minute or two. How do those salts behave, right? What do we think about what's going to happen? Yeah. Okay, save your thoughts. All right, so what were we thinking? And so yeah, Hunter was kind of giving us a preview. So did people follow what he said? What were you thinking? What happens? What was he implying when talking about fluoride? Acidic, basic, or neutral? So do you want to repeat what you said?
So, fluorine, when it's in its standard isolated state like that, and it's in a solution of water, it's going to want to form hydrogen fluoride or HF.
And then what's the other product too?
OH.
Yeah, so what does that tell us? So going back to this, is it acidic, basic, neutral?
I guess it's basic.
Yep, so right, it's a basic salt then. And so now thinking of solubility, right, well, if it's with a bunch of hydroxides, well, that's not going to be, right, favorable for it to be in solution. We already have hydroxides, so that's not going to make it soluble. Versus kind of thinking about, too, what's going to happen in acidic conditions, right? In acidic conditions, obviously we have excess hydronium, or H+, so it's going to definitely make HF and leave us with water, right, which will not affect our solubility. So then, yes, we want to say, especially since, again, fluoride is our basic salt, so that means it's going to be more soluble in acidic conditions.
Is that because the anion is acidic?
Because the anion's basic, right? So then it has more of a tendency to react with the acidic, right? Like we saw to, again, make HF. We just don't want to make a bunch of hydroxides, right? And then have more hydroxides in solution. Then that's not going to be favorable. And, right, we need this because you're kind of thinking about, this is also almost like a two-step equilibrium, right? Because we have to think about barium fluoride disassociating, but then if we want to keep pushing that equilibrium to the right, we have to keep fluoride consumed and moving and doing something else, such as making HF, right? But then it's not going to make HF if there's a ton of hydroxide forming in solution, right? That's going to push the equilibrium back, which then affects our solubility. All right, do you want to take a break now, or do you want to finish up B and C? Okay, let's finish up B and C. So then looking at silver iodide, so again, take a minute, acidic, basic, or neutral. So what do we think about silver iodide? So is silver acidic, basic, neutral? So it should be neutral. So if anything, right, a metal cation could potentially be acidic, right? If we remember that kind of from our aluminum 3+, right? Those are considered acidic. But silver's just 1+, so it's neutral. And then what about iodide? What acid does that come from? So HI, right? Look back at your chart if you need to. Does that fully disassociate? So yes, fully disassociates, so that means that it is neutral. So really no effect with acidic, basic, or neutral. All right, so let's look at the last one. So this should be a little easier. So now calcium hydroxide. So again, that's a little more straightforward, just thinking about the simple first disassociation. And so what's going to be more favorable, acidic, basic, or neutral conditions? So probably not neutral, because what do you want to do? Again, you're thinking about how can I push this reaction to the right. So if we want to push it to the right, we probably want to remove hydroxide by some method. So then what would that make it? What reacts with hydroxide?
You would have to have some source of hydrogen or hydrogen.
Yeah, or acid, yeah. So yeah, acidic solution. So acidic solution would work, again, right, thinking about how this hydroxide is going to go on to react with some acid to make water, of course. So again, right, you're kind of thinking in systems of equilibrium as well, right? So we want to drive this, again, forward. So how can we react this? Or later, right, we might see how can we form a complex to get rid of it. All right, so let's take our 10-minute break. So be back, I don't know, 12:06, 12:07-ish roughly.
Hydroxide wants to form water, it doesn't really like hydroxide, it wants to be water, so if you do the same equation with hydroxide, you should put it up there. Both the molecules are happy to form more of the, they will dissolve more because there's less resistance. I'll tell you about the actual
All right, let's continue. All right, so now we're thinking about precipitation. And so again, right now we can actually start quantifying when precipitation is going to occur. And so, okay, let's just obviously first define precipitation from a more mathematical sense. So of course, precipitation will occur when our concentration of ions, right, exceed our solubility. So again, this is why we're getting back at, we have our KSP, we have how to calculate our molar solubility. And then other kind of concepts, right, from the past. So we have our Q, right? So again, saying we can look at our snapshot, kind of look at where is our system. And then, right, we can, of course, compare that to KSP. And then, of course, determine whether precipitation will occur or not. And then again, just defining the different points. So if Q is equal to our KSP, then the solution is saturated, so no precipitation will occur. So right, just right on that edge. So we can say, right, it's fully saturated at the limit. And then, of course, if Q is under that, then we know our solution is still unsaturated. So then we would have no precipitation. And then, of course, if our snapshot Q is greater than our KSP, then we're past, right, what's allowed. And so now, yes, we will have precipitation. And so sometimes, and again, right, I think YouTube has a lot of good videos of this. I can always dig some up if y'all haven't seen them, of, right, these supersaturated solutions, especially people playing with like water and all sorts of things where it freezes right at those limits. And so again, right, just kind of thinking about how this plays out in lab. So again, just kind of thinking about, okay, we have our sodium chromate solution plus silver nitrate. That gives us silver chromate, which is that nice red precipitate.
Do supersaturated solutions have any like technological use, or are they too unstable to utilize in like an engineering sense?
Oh, I wouldn't know about that, yeah. Because, I mean, that's just talking about saturation and, like, right, crystallization. But, I mean, kind of thinking, I'm just thinking of batteries. It's like they're trying to get, though, to those, like, ionic liquids anyways, and, like, trying to make things that are, like, ionic and liquid and, like, that have weird properties. So, yeah, kind of different veins of thoughts there, but yeah, these thoughts are kind of better suited for like water solubility, water purification. Again, kind of going back to like even how and this could have been another field trip idea. I think there's like the Medford water treatment plant, so we could visit there. But yeah, they have to balance out different ions. So I'm sure that's why they make different decisions of like, do we buffer with sodium carbonate versus like sodium hydroxide? So that sort of thing. And so we also have, again, looking at how to crystallize stuff. So a supersaturated solution will precipitate if you add a seed crystal, or again, just concentrate it down over time. And so this is a little bit rapid nucleation. You can tell from how like feathery these crystals are as well. And so again, right, if you have some point of nucleation, like another crystal, then that can cause, right, other crystals to kind of grow on it. All right, so now let's look at some problems here. So we have a solution contains lead nitrate, and it is mixed with one containing sodium bromide to form a solution that is 0.015 molar in lead nitrate and 0.0035 molar in sodium bromide. So do we have a precipitate. So before I kind of go through how to approach this, just kind of think for a second, right, how we might go through this. So kind of what reactions are relevant, right, what solubilities are relevant, and then we'll go through it together. What do we need to set up? Yeah, so we could use our rice table, or even, we don't necessarily have to get too into it, but what do we need to set up? What should we plug in?
We can put together we would need the case today for the K value for this lead salt here.
Yeah, so we need, so lead bromide. So now putting the pieces together, so let's check that. So lead bromide, so 4.67 times 10 to the negative 6. Okay. Now what else? So you mentioned rice table, but yeah, so we could think about that, but not only, right, not just our rice table, but just trying to get at what is our equilibrium expression. So what's our KSP expression?
It's going to be 4s cubed equals KSP.
Well, just even more generalized, because that's like molar solubility, right? But we don't want molar solubility. We're trying to figure out, will these precipitate? So what do we need to plug into? So we do need to find Q. So, right, so that means we need to plug that into our KSP. So, right, so we have our KSP expression just like before. And so correct, right, we're not trying to find equilibrium right now. We're saying, okay, this is our expression. So then let's find Q. Right, so then, I don't know, I'll call this QSP. So, right, just plugging into our expression. So we're given, and so again, right now we can translate this. Again, think about how much is going to disassociate. Well, just one equivalent of lead. So that's 0.015 molar concentration of lead. So now we can plug that in. And then our bromine. And so it's sodium bromide, right? So just one equivalent of bromine disassociates, so 0.0035 molar for our bromine concentration. So does that make sense to everybody how we got here? And so yes, let's just plug this in now to get our actual Q value, right, to compare to our KSP. 0.015 and 0.0035 squared.
Finding the Q value is exactly like finding the K value, except you're using the concentrations you're given.
Yeah, because again, right, we're just finding the snapshot. So we're not saying we're at equilibrium, we're not at max solubility, right? We're just here. And so then we get our Q value. So I get 1.84 then times 10 to the negative 7.
That's what I got.
Perfect. And then, so now, right, let's compare that. So I'm looking at negative 7 roughly versus negative 6. So are we at the saturation limit?
No, we're less than the saturation limit.
So Q is less than K, and so we will not get a precipitate. So no precipitate. Yeah.
Is there a difference between precipitate and precipitant?
I don't think so. Unless, well, now it sounded like you said participant, like somebody who's participating. Yeah, precipitate. Okay. And again, so now we can think about maybe again water quality or something. At least that's what I'm always thinking of for some reason. Probably just because it's like tiny concentrations of stuff, so that's the only time when you care about tiny concentrations is water quality. And so, right, thinking about purification of especially, right, heavy metals, how do you get heavy metals out of solution? Well, if we have different cations, right, we can separate them by the addition of some reagent that will get an insoluble salt with some ions and not others, right? So then we can have this kind of selective solubility. You can separate, again, if you're trying to quantify these cations, that could be a way to separate them, right? You collect them, then you can physically have them in your hand, quantify how much was in that, or again, right, do a series of these to do some sort of water quality. And so again, sometimes you could have a reagent that precipitates out with more than these cations. And so as long as their KSP values are different though, right, you can still do this selective precipitation. And so we'll see that right now. All right, so let's look at this. And again, we have to kind of think about what information we need. And so, okay, it's telling us that we have magnesium and calcium ions are present in seawater. And so we have, looks like it's giving us the initial concentration of magnesium of 0.059 molarity, and calcium is 0.011 molarity. And so they can be separated by selective precipitation with KOH. And then it's asking us what minimum hydroxide triggers the precipitation of magnesium. All right, so again, let's kind of think about what values we need. And so eventually we might need calcium hydroxide. I'm just kind of putting it to the side. And definitely, right, we're going to start off with magnesium hydroxide. It's asking about that first. So let's get our KSP for magnesium hydroxide. So 2.06 times 10 to the negative 13 for magnesium hydroxide. KSP 2.06 times 10 to the negative 13, I believe. Sorry, just double check that. All right, so then what do we have to set up here? What's our equation? And you could also give me, right, maybe what's our KSP expression?
Is it implied by the problem that the magnesium is in another form?
Sorry, what?
Is it implied by the problem that the magnesium is in the form of magnesium hydroxide and it's in the water?
Well, right, that's what it's telling us that we're trying to precipitate out, right?
Yeah.
So it's not in this form in the water, but it's saying we're going to add hydroxide to it to precipitate out magnesium hydroxide. Yeah, and remove the magnesium, right? So again, you're kind of thinking about what if you were trying to treat this water, you're trying to get at this magnesium, and so the solution is to add hydroxide. And so again, right, we're trying to figure out minimum hydroxide, because again, right, thinking about pH, and you don't want to alter the water pH too much. So you want to get your minimum amount. So how do we find that? What should we plug it into? We have the KSP value, right? So we should probably set up, maybe we want our rice table to at least kind of help us see our reaction. Oops. So again, right, thinking about our dissociation and those two equivalents of hydroxide. And then I would write out our KSP. So magnesium 2 plus to the 1 power times hydroxide to the second. And so where do we go from here? So not Q, right? But we have, so we have kind of one value, right? We're trying to find hydroxide. But then, so we can just plug it in, right?
Yeah.
Yeah, so let's plug it in. So we have all our values. So we are trying to find, right, again, minimum hydroxide concentration. So now KSP, so 2.06 times 10 to the negative 13 is equal to, so we said we had 0.059 initial concentration of magnesium. Trying to find x squared here. And so now help check my math. Oh. So again, double check me on this number. Make sure I didn't make a algebra. You got that? Everybody got that? So I think that's our consensus. So right now we're saying a 1.87 then. So 1.87 times 10 to the negative 6 molar concentration of hydroxide, right, will cause precipitation. All right, good. All right, so now let's continue this problem. And so now let's ask a different question. So we want to continue with this extension, again, kind of thinking about selective solubility. And so now we want to ask ourselves, so at what concentration, because right, we should compare this to our calcium. So now we want to know at what concentration of hydroxide ions will calcium hydroxide precipitate out. So think about how you would do that. So try to start that. I can scroll up and down. I guess we should look at the KSP together. So calcium hydroxide looks like it's 4.68 times 10 to the negative 6. So KSP, calcium hydroxide, 4.68 times 10 to the negative 6. And I can scroll back up. So again, we had an initial concentration of 0.011 molarity of calcium. So see if you can go from there. All right, so how's this going? Kind of walk me through what do we know?
We have the number of moles, the molarity of the solution, and we have the KSP, and we have one unknown, so we can solve the unknown.
So let's do that. So, right, looks just like before. I'm just writing out the disassociation to be explicit, and then writing out the KSP expression. All right, so then you said let's just plug it in and solve, so it looks pretty similar to what we did before. So 10 to the negative 6, 0.001 to the power of 1 times x squared. And so now y'all can tell me what you got for x while I finish plugging it in.
I got like 0.0206.
0.0206, perfect. So it looks like I got the same thing. So everybody on the same page. So excellent. So right now we're saying a much higher concentration. So 0.0206 molarity. Then, okay. And so again, right, we're kind of thinking about this in context, kind of what's going on, right, how this is going to work. So we're saying we can precipitate out our magnesium with this molar concentration, right? And then, okay, well, we can precipitate out our calcium then. But then we just want to check, and again, this helps us to kind of verify, do we have an effective separation? And so now we can also calculate, and again, you'll kind of have to think about what to plug in. And so what will the concentration of magnesium ions be in solution when calcium, oops, I don't know why I wrote calcium, when calcium hydroxide is precipitating out? So kind of think about what we just found too. We'll go over it. So how is this one going? Do we figure out kind of what we needed to plug in?
My first thought was that you would plug in the answer from the previous problem.
Yep. So, right, that's what we want to do. So, right, we're still thinking of this general reaction, right? But then kind of what it's saying and what the key was is, okay, right, we had said this is when our calcium hydroxide was going to precipitate out. So, okay, this is our concentration of hydroxide. So again, right at this point, our molar concentration of hydroxide is so. So yes, just like he was saying, okay, let's go back, right? That's what it's asking us to do now, is we can go back, plug it back into our magnesium KSP expression, and then figure out, right, how much magnesium is still left in there. So let's work through that. Oops, and I forgot our KSP again for magnesium. So 2.06. Right, equals our KSP of magnesium, so magnesium concentration times hydroxide squared. And so again, right, plugging in the current hydroxide value. And so let's see how this looks. So now 0.206 squared, and so again, just double check my algebra here. So I get this answer for my magnesium concentration. Is that what you got? I could have always made a typo. Some yeses, some nos.
Yeah, that's right.
So it looks like, and again, so look at how tiny that number is now. So we have X is 4.85 times 10 to the negative 10 molarity here for our magnesium. And so, right, very, very small. So I would say, and again, right, we can look at what we started with. So we started with 0.059 molarity. We're now down to a factor of negative 10. So, right, we could say, yes, this is an effective separation. And so, of course, right, this was a good example kind of set up. But again, right, you might think of another scenario where if they're molar solubilities, and you can, right, kind of, again, get a sense for that. We have -6 versus -13. So pretty large order of magnitude difference, right? So, of course, the better the order of magnitude difference is, right, the better the separation. So just keep that in mind. Obviously, as they get closer, it's going to be more difficult and not as effective. So just things to keep in mind in terms of trying to figure out, right, the appropriate counter ion like hydroxide. All right, I guess let's kind of keep going for a little bit at least with our complex ion formation. Again, kind of our same thoughts here. And so now we're kind of thinking about these different complexes, and we're starting to get into somewhat of inorganic transition metal chemistry, or at least very basics. And so like we had mentioned, so our transition metals tend to be good Lewis acids. So that means, right, again, they want to accept electrons. So let's remember, right, the definition of a Lewis acid and a Lewis base, right? So we said our acid is going to be, right, our electron acceptor. So transition metals, right, want electrons. And then our Lewis base, right, tends to be our electron donor.
How do these terms differ from cation and anion? Is it synonymous?
I mean, it's not synonymous, right, but they're somewhat related, right? So like we're kind of seeing, well, a cation is going to have more of a tendency to accept those electrons, right? But it's also just how it's kind of behaving. So that's also what dictates, right, our Lewis acids, because it has to be some sort of scenario, which let's look at right here, right? So what happens in this ligand formation is, right, so now it's telling us that they tend to bond these water molecules. So let's think about how that happens, right, and what is exactly going on with our definition. And so, okay, they use silver, so let's just stick with silver here. And so again, right, water is acting as our Lewis base. So just drawing out our basic Lewis dot structure. So of course there are our electrons, right? That's where the action's going to occur. So what's literally going on with this ligand formation is these two electrons are donating to silver like that. And so let me kind of redraw that. And let's actually draw out, because right from our reaction here, it's indicating that this silver actually will coordinate two equivalents of our water, again, acting as a ligand here. And then notice in this case, right, the charge doesn't change. So of course, water is neutral. So that's why it's not going to influence, right, our overall charge. And so now let me just rewrite that. So again, thinking about how it's attached. So it's attached at the oxygen, right? It still has one lone pair. And so it may not always be drawn like so with this dative bond. But again, I'm just emphasizing that to show that this is a bond where the oxygen is donating both electrons. So that's not a normal bond. Again, the definition of a normal bond, each one contributes one electron.
In your experience, have you seen like crystal structures or recursion with this kind of stuff in terms of like complex structures?
Wait, sorry, too general of a question.
Oh.
Like, yes, that is literally the entire field of inorganic chemistry is like shit attached to metals.
Okay. And I guess I'm asking if this has the potential for forming a pattern and forming a larger crystal.
Like it really depends like what is happening, right? So like, because now we get into like the ligand, scaffold, and yeah, so like down the rabbit hole pretty quickly, because right, like so many things can be a ligand is what we're going to see. And you can have kind of like these most basic complexes. So let me just pull up kind of the most famous example, which we may talk about later. I don't quite remember. But there's these like Werner's complexes. Oh, geez, this was not the most. Okay, here we go. But, right, they have Werner's complexes. These are pretty famous because they have really distinct crystal forms, aka one is red, one is green. So, yay, pretty shiny colors. But, right, look at how simple these ligands are. We have our ammonia acting as ligands, right? So this is just ammonia. Again, think about ammonia as a base. Again, dative bond, those two electrons are being donated to cobalt. And then we can also have halides acting as ligands. So in this case, right, again, just donating its electrons there to chlorine, and to cobalt, sorry. And again, right, just the difference in position. So that's the whole fascinating thing about Werner's complexes, yada, yada, yada. Different positions, right? But we're just saying this is a complex, this is a ligand, right? They can make crown ether complexes, right? This one I think just has magnesium in there, or potassium, but you could stick metals in there, like people try to do that. So like a ligand is just super broad, right? So like there's a billion ligands that we could talk about. So yes, I've seen plenty of crystal structures. And so again, this is just a very, very, very broad term. It's just anything that we can attach to a metal is called a ligand. Again, right, this can be a complex structure. We won't go down the rabbit hole of ligands. And so what we're trying to get at, though, is, okay, well, we want to have our formation constant, Kf. And so now, right, this is saying basically how much does it take to complex? How favorable is that? And so we can quantify this in the sense of silver in ammonia, for example. And so again, right, tends to coordinate two equivalents of ammonia. And so then we end up with our Kf expression, so our complex as our product over the two ions, right, that went into that. And so again, right, follows pretty simply for our equilibrium expressions, kind of what we're used to. And so here is, again, just some examples. Again, obviously, right, these are simple ligands and simple complexes that we're forming. So again, could also be thinking of how to purify stuff, to try to move things out of solution, equilibrium expressions, or just control different formations. So again, just kind of take that in. All right, we probably don't have time to do this. So let's just kind of read through this, and then we can chew on it, right, how we would approach this, and then we'll pick up here with a warm-up, right? So again, just kind of thinking of how we're going to set it up. So we have a 200 milliliter sample of a solution that has 1.5 times 10 to the negative 3 molarity in copper nitrate. And then you have 250 mils of a solution that's 0.2 molar in ammonia. And so then it asks us, after the solution reaches equilibrium, what concentration of copper remains. And so this is a little tricky one, right? But at least, again, we'll stop here. But just kind of thinking of what is even going to form, right? So that's kind of your first step. So you have copper, you have ammonia. So then the first thing you want to just do, right, is look at this chart. And so, right, we have our copper tetraammonium species. All right, so we'll kind of leave there with the last few thoughts, because again, kind of think about how this is going to set up, maybe do a reaction, hint, hint, maybe have to find moles, perhaps, hint, hint. But yeah, so we'll pick up with this on Thursday. I'll leave this up here, and then if you all have any questions, more than happy. Oh yeah, sorry, I forgot to post the live link. Yeah, homework.
I do need to watch that in the lab, and I'll have a question.
Oh, yeah, that's fine.
Or you could be like, oh no, I mean, this little.
Question for you real quick. So I'm not gonna be here in class on Thursday. Would it be easier if I just bring it to lab today to work on it, or should I?
Yeah, I would do that if you
Okay.
can,
If
yeah.
there's spots available. I'm not
Oh,
sure.
there's spots, yeah.
Okay, so I can do that then.
Yeah.
Perfect.
Oops. All right, so the live notes should be up now. Just let me know if they don't function. And I will stop this stream and see y'all in lab.